Okay, we're going to go over this presentation, which is the presentation number 9. The name is SARIMA models. SARIMA stands for Seasonal Autoregressive Integrated Moving Average Models. Okay, and we just call them SARIMA models, or Seasonal Autoregressive Integrated Moving Average Models. And it's a combination of what we've already seen as ARIMA models, which have combined the autoregressive components and the moving average components. It combines both components, but also it includes a seasonal component. Okay, many of the time series that we observe in practice behave. They have some seasonal pattern, particularly in economics and in business, for example, sales of stuff and things like that. They normally show some type of seasonal behavior. So let's go over these models and see how they come up. So again, we've mentioned that seasonal series is one that has, in addition to having a trend, okay, for example, they may have a trend and long-term cycles. We have fluctuations that repeat periodically within a year, for example. Okay, so maybe within a year we have something that's happening every quarter, or something that's happening every summer or every end of year. And this is type of behavior that things like sales of beer, for example, increase in summer, sales of toys increasing by the end of the year, for the beginning of the next, and so on. So those are seasonal behaviors. We will be referring to the seasonal period as with the letter A, with a capital A. Okay, so E is with a capital E. Sorry, with a capital E. So E is not necessarily 12. If we have monthly data, it could be 12, but it could also be 6 months, or it could be also 3 months. I could have seasonality of 1 quarter, or seasonality of 1 semester, or seasonality for a year. Okay, so E can be anything, and depending on whether we have monthly data or not. For example, if we have weekly data, we may have seasonality every week. For example, if you look at consumption in bars increase by the end of the week, and they have very lower values at the beginning of the week, and they always increase by the end of the week. Well, except with this situation we're living now. Although now bars are open, and it doesn't matter which if the stoplight is in green or yellow or orange now. Okay, so we can have different types of seasonality. We'll call the seasonality period as capital E. Now, the same way we have a difference operator that applies to that we have been using to remove trend. We've taken a difference to remove trend. Sometimes we may have to take 2 differences. Sometimes we need also to remove a trend that's seasonal, and then we are forced to take seasonal differences. We will denote the kth seasonal difference of order E, okay, or of seasonality E. So that will be the kth order difference of seasonality E as 1 minus B to the E, which is the seasonality period, and all that raised to the kth power, which is the number of differences we're going to take. Okay. Now you can show that this difference is given by the sum from j equals 0 to k of k factorial divided by j factorial, k minus j factorial, times -1 to the j, zt minus j times e. So if you look here, this is involving zt, and then if j is equal to 0 is zt, if j is equal to 1, it will be ct minus e. If j is equal to 2, will be ct minus 2e and so on. Okay, so we're taking observations e periods behind than when we are at time t. Necessarily, if we have, let's say we have monthly data and I have a seasonality of 12. Well, if I have seasonality of 12, that means that I will be taking an observation at time t and subtract the observation at time t minus 12. And therefore, I will be losing 12 observations. So it will be very, very strange that we need to have more than 1 or 2 seasonal differences. In most cases, at most, we will have 1 seasonal difference. Because again, if we have to take 2 seasonal differences, we're going to lose 24 observations. That's a lot of data that we'll be losing if we need to take 2 times a seasonal difference of 12. Now, a backshift, the same way we have the backshift polynomial for a series that does not have a seasonal component, we will define a backshift polynomial for a seasonal series. So if I have a seasonal series with seasonality e, we will define the g of b polynomial as g of b to the e polynomial. That's the notation we'll be using, g of b to the e. And it's essentially 1 minus g1b minus g2b squared minus g2b 2 times b raised to the 2e power up to jk b to the k times e power. Okay, so that will be a polynomial of backshift polynomial of with seasonality e. So that's the definition that we'll be using for the seasonal polynomials. For example, suppose that you have seasonality equal to 12 and k is equal to 12. That is, you want to take a second seasonal difference of order 12. So that again, that's denoted by a second order difference of seasonality 12. And that will be 1 minus b to the 12 squared, and that will give you zt minus 2 times zt minus 12 plus zt minus 24. So I'm using, I'm taking a second order difference, seasonality 12. So I will need to start the analysis, I will need the first 24 observations that will not be able to use in the model, because I need to take those the observations in the lagged 12 and 24 periods behind. Okay. And the polynomial in this case would be g of b to the 12 will denote by g1 minus g1 b to the 12 minus g2 b to the 24th, and that will be zt minus g1 ct minus 2 minus 12, sorry, and zt minus 24 times g2. So my g's are going to play the role later as the parameters of the models. Okay, but that's again, first we're going to be dealing with purely seasonal models, and then we'll combine them with ARIMA models. Okay. Now, let's suppose if you look at the consumer price index in Mexico from January 2011 through December 2016, if we take a seasonal difference of order 12, of seasonality 12, order 1, we're going to lose 12 observations. Okay, here's my data. And now if I'm going to take a seasonal difference of seasonality 12, I'm going to miss all these observations, because if you look, this observation 4.056 is 104.284 minus 104.284 minus 100.228. That difference between this minus this minus this is giving you 4.056. And this one will be the difference between that, between 104.496 and 100.604. So that when once I take the difference, I'm losing 12 observations. If I were to take a second order difference, I would be losing 24 observations. Now, in general, we apply the difference operator, seasonality E, order D, capital D, and we'll use capital D to denote the number of seasonal difference, okay? So we have been using D to denote the number of, let's call it standard differences. And capital D will be used for the number of seasonal differences. Okay, that's standard notation. We'll use capital D for the standard, for the seasonal differences. Okay. Now, it is possible to find series that may have a purely seasonal behavior, and those are the first ones that we're going to study. I may have a series that has only seasonal behavior. That's possible. If I have a series that only has a seasonal behavior, I can use what we learned from ARIMA models to model a SARIMA, okay? A seasonal, purely seasonal model. We would denote that by purely seasonal model as SARIMA. P, capital P, will be the order of the autoregressive polynomial for the seasonal series. D, capital D, is the number of differences that we take, and Q is the order of the moving average polynomial for the seasonal series. So that model will be written like this. We will use capital Phi to denote the autoregressive polynomial, and we will use capital theta to denote the moving average polynomial. Okay. Remember that if we do not have seasonality, we are using, without seasonality, we are using phi of B delta to the D, the difference operator to the D, Ct minus mu equals to theta of B AT. Okay, so there's no, when we do not have seasonality, it's equivalent to having E is equal to 1. Okay, so we use capital letters to denote the seasonal model. And again, we'll start discussing the first purely seasonal model, and then we'll extend that to have a model that combines seasonal behavior with non-seasonal behavior. Let's consider a simple process first. Let's consider the SARIMA. I missed an S here. It should be SARIMA. Let's consider a SARIMA process of orders 1, 0, and a seasonality E. That is, I have an autoregressive seasonal model, purely autoregressive seasonal model. Then this model, I can write it as Z tilde. Remember, Z tilde is ZT minus mu. Okay, we already subtracted the mean. Is capital Phi of ZT minus C times CT minus C plus AT. So this model here would be, capital Phi of B to the E times the difference here, the E will be, or I'm sorry, theta. I forgot it. I put a phi here. It should be a theta. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . theta of B to the E AT. Okay. So if I have a seasonal model for order D and I only have one autoregressive term, then this model will become 1 minus phi B. And I do not have, as I have zero differences here, so I don't have this difference operator, and that's equal to, and theta of B is what? Theta B is just 1 because of my order for the moving average polynomial is 0, so it'll be AT. And from that I get ZT is equal to this thing here. That's so it's this model is telling me ZT, my observation at time t depends on my observation at time t minus e plus random noise. Okay. For this simple model, we can compute very easily the variance and the covariance function. The variance will be, I already subtracted the mean. So the variance would be expected value of phi, capital Phi ZT minus C plus AT, the whole thing squared. And if I square this polynomial, I get phi squared times expected value of ZT minus C squared plus 2 times phi expected value of ZT minus C times AT plus expected value of the AT squared. Okay. Now, expected value of AT squared is equal to what? Any guesses? Anybody? I'm not seeing your faces, so don't worry. I will not know who answered. Are you awake, guys?
Yeah, but I don't know.
Well, remember the ATs are what? Are white noise. They're independent. They're identically distributed with mean zero and
The
variance.
term from the middle is 0.
That'll be the variance, right? Expected value of AT squared. This term is the expected value of AT minus expected value of AT, which is 0 squared, right? And that's the variance that we have denoted by sigma squared today. Okay. Now, what happens with this term here? ZT minus E depends on what? On ZT, on AT minus E, but it doesn't depend on AT. So this term should disappear, right? And then here we have the gamma, expected value of ZT minus C squared is equal to phi gamma 0 times phi squared. Then this term becomes 0, and I only have the sum of this term, which is this one, is this one here, and this one is sigma squared. So it looks exactly the same as in AR1 model. So gamma 0 is capital Phi squared gamma 0 plus sigma squared. And that's sigma squared divided by 1 minus capital Phi squared. Remember, in an AR1, remember, in an AR1 model, what was gamma 0? Gamma 0 was equal to sigma squared divided by 1 minus phi squared. Right. So it's very similar, except that now I have seasonality, okay? But the behavior of this thing, the gamma 0, will be behaving like in a similar way that it behaved in the traditional AR1 model, the non-seasonal AR1 model. The same way we did this thing, we can calculate now the variance covariance function, the variance covariance for capital E, for E periods ahead. Okay, so gamma sub E would be the expected value of what would be this gamma sub B? Gamma sub B, remember, gamma is just go to the definition. Gamma sub B is the covariance between ZT and CT minus E, right? Or CT plus E, it doesn't matter. So this will be equal to what? This will be the expected value of phi ZT plus AT times phi CT minus E or plus E, it doesn't matter, plus AT. I'm just replacing what the equation for ZT and CT minus E is, right? So that when I compute the covariance E periods away, E periods apart, I'm going to get phi times sigma squared, which is this term here, over 1 minus phi squared, just like we did in the AR1 model. When we looked at the AR1, in the AR1 model, we got that gamma 1 was equal to phi times sigma squared divided by 1 minus phi squared. That's what we got in the AR1 model. So it's a very similar situation here. Then gamma 2e, if we're 2e periods ahead, or 2e periods behind, I just have a square of this phi. This phi just keeps multiplying it by itself as for as many times that we are using e, that we're separating observation t from t minus e, t minus 2e, t minus 3e, and so on. Okay. And then for any multiple of e, this will be the expression for the covariance between ZT and ZT minus E, or ZT and ZT plus E. The covariance function is symmetric because of the way it's computed. So, and again, remember, we're working with models that are stationary. So the behavior will be the same regardless of T. So gamma I gamma I times E, that is I times E periods away or apart, will be phi to the I, which is the number of periods that I'm looking at, the number of periods apart between the two observations. And that will be this expression for I greater than or equal to 0. While for anything that's not a multiple of E, anything that's not a multiple of E, we will have that the autocovariance is going to be equal to 0. If I have any sub-index there, which indicates the number of lags apart, that is different from a multiple of E, the covariance will be 0. So, for example, if E is equal to 12, then we'll have gamma 12 will be phi squared, capital phi, sorry, capital phi. Oops, I didn't erase it. That will be capital phi times sigma squared divided by 1 minus phi squared, right? And this is gamma 0, right? That's gamma 0. Gamma 24 would be phi, capital Phi squared, gamma 0, and so on. But if you look at any other gamma sub 2, for example, gamma sub 2, the covariance between ZT and ZT minus 2 will be 0. Let's look at that example here. Is that clear, or do you want me to go over a little example here, assuming that E is equal to 12, for example.
Yes, could you do an example?
Okay. Let me erase this thing. Okay. Let's look at this case where E is equal to 12. If E is equal to 12, then the first gamma 0 is it clear so far that gamma 0 is equal to this term here, sigma squared divided by 1 minus phi squared? See, because I have this thing here is phi squared times gamma 0, because the gamma 0 is the variance, and the variance is the expected value. Since I already subtracted the mean, this is the variance. This thing here is the variance, gamma 0. This we already saw that it's equal to 0, and this is sigma squared sub A. So this, up to this point, my guess is that it's clear that gamma 0 is actually equal to sigma squared divided by 1 minus phi squared. Are we okay up to this point?
Yes.
Okay.
Yeah, we're good.
Okay, let me change now I'm going to use E equal to 4 so that I have to work less terms here. Let's suppose that A is equal to 4. Okay, we already know then that gamma naught, the variance is sigma squared divided by 1 minus phi squared. Now let's look at gamma 1. Gamma 1 is equal to, remember, gamma 1 is expected value of what? Of ZT times ZT minus 1. ZT minus its mean minus ZT times ZT minus 1. Now ZT is equal to what? ZT is equal to phi ZT minus E plus AT, because that's the definition of ZT, ZT minus E times AT, and then times phi, and then what's the definition of ZT minus 1? It'll be phi ZT minus 1 minus E plus AT. That would be gamma 1, the covariance between ZT and ZT minus 1, or ZT and ZT plus 1, because it's symmetric. Okay, so if I do this product, that will be what? The expected value of, and then I have phi ZT minus E, right? Let me here, ZT minus E times phi ZT minus 1 minus E, right? And then I have so it's this one times this one. Then I have ZT minus E. I'm sorry, this is an AT minus 1. Sorry, here. Let me make a correction here. This is AT minus 1. Okay. And then I multiply ZT minus C times Z. I put an E here, and it's not an E. I know it's here, but we'll say, then I have what? CT plus phi CT minus E times AT minus 1. Okay, and I'm going to replace the E by 4 so that it's easier to see what's going on. I'm going to say here T minus 4. And I'm going to say here also T minus 4, T minus 1 minus 4. And here it's going to be T minus 4, AT minus 1. Okay. And then I only have to multiply now AT times AT minus 1, right? And this times this, that will be 8 plus 5 AT times ZT minus 1 minus 4. I'm replacing the E by 4. And then the square plus AT times AT minus 1. Okay, now look at this thing here. ZT minus 4 depends on what? Depends on ZT, depends on AT, and AT minus 1 and AT minus 2 and so on. Whereas ZT minus 1 depends on AT minus 1, AT minus 2, AT minus 3, and so on. So these two have mean 0, and these do not depend on on anything that involves this one here. So that expected value is going to be 0, right? Now this one, ZT minus 4. ZT minus 4 depends on AT. If I have a ZT minus 4, that will be depend on AT minus 4, but doesn't depend on AT minus 1. So this will also be 0. So this is 0. This is 0. And the same thing happens here. ZT minus 1 minus 4 does not depend on AT, and the expected value of AT is 0. So that's also 0. And this, since the ATs are independent and they have mean 0, the expected value is the product of expected values, which is also 0. So that's going to be equal to 0. Gamma 1 is equal to 0. Do the same thing for gamma 2. You'll find that gamma 2 is equal to 0. Just replace the corresponding equations, compute the expected value, and we'll see that gamma 3 equal to 0. What changes is when you go to gamma 4. Because when you go to gamma 4, then you will have the expected value of ZT. Let me erase this thing and put it over here. See, gamma 4 would be equal to the expected value of what? Expected value of ZT times ZT minus 4. Now, ZT is 5. ZT minus 4. I'm not putting the wiggle here in the Z, but assuming that I'm not putting that, but assume that I'm putting all those things, okay? It's expected value of this thing times 5, and then ZT minus, if I have ZT minus 4 here, that will be ZT minus 4 minus E, right? ZT minus 4 minus E, I'm sorry, minus 4 minus 4. Minus 4. Minus 4 minus 4. And I do the same thing with the other product, plus the expected, plus 5 CT minus 4 times 5, so I'll get a 5 square here, ZT minus 4 minus 4 plus pi, and then I will have AT ZT minus 4 plus AT times AT minus 4. Okay. So that will be equal to, see here, this is going to be 0 again. This is going to be 0. And then here, look at what I have here. I have 5 ZT minus 4, ZT minus 4 minus 4. that will be the expected value of this thing will also be 0, okay, because that depends on 80 minus, this depends on 80 minus 1, 80 and 80 minus 1, and so on. Doesn't depend on 80 minus 4 minus 4, let's say. So this will be 0. And here I will have gamma. This is the covariance between, this is this will be the variance, I'm sorry, this is GT minus 4, and this is CT, no, the minus 4 doesn't go here. This minus 4 doesn't go here, because what I get is that will be the variance. This will be 0, this will be 0, and this will be then, this will be equal to phi times the variance, gamma 0, which is expected value of the product of these two, is gamma 0, is the variance. Okay, so pick any E, and you'll see that the autocorrelation function for a purely seasonal model behaves very much like the autocorrelation function of an AR model. See, the AR1 model, its autocorrelation function, this is the covariance, but we need to divide by the variance, and that's it. We have the autocorrelation. Remember that for the AR1 model, the autocorrelation function looked like this. We have, this was phi, this will be phi squared, phi cubed, and so on. Now, like 1, 2, 3, 4. In a seasonal case, if my seasonality is 4, if E is equal to 4, I will have something like this. It's period 1, 2, 3, and 4, 5, 6, 7, and 8. So my autocorrelation function will be decaying, but it will be only different from 0 at lags that correspond to the seasonality period. Okay. So all you have to do is replace the definition of ZT and then compute the expectations. So rho sub k, since I'm dividing, remember gamma k was equal to phi to the k, so I'm sorry, phi to the k gamma 0, we have gamma 0, and we have that gamma E was equal to phi gamma 0, and gamma 2 times E will be equal to phi squared times gamma 0. So the autocorrelations will be, of course, rho 0 is 1 always, but rho 1 would be this phi gamma 0, phi capital Phi, divided by gamma 0. So it will only be phi. And gamma and rho 2 will be phi squared, and so on, which is the same behavior that we have for an AR1 model, okay? A non-seasonal AR1 model. Okay. That's the behavior of the autocorrelation function. For example, if we have this model where ZT is equal to 0.6 ZT minus 4 plus AT. And if we have sigma squared equals to 1 in this particular example, we would have rho k is equal to 0.6 to the k, for k equals to any multiple of E of the seasonality period, and 0 for k different from IE. So if k is different from a multiplier, from multiple of E, then the autocorrelation is going to be 0. So the autocorrelation function is going to look like this. This is for this model. This will be the autocorrelation function. At lag 0 is always 1. Now here I have 0.6, and then I'm sorry, 0.6, 0.6 squared, and so on. That will be the autocorrelation, the rho sub k. So it looks like the autocorrelation function for an AR1, except that they are like the autocorrelations that are different from 0 are E lags apart. E is equal to 4, so they're They occur at lag 4, at lag 8, at lag 12, and so on. That's where they will occur. But the behavior is very similar. Now let's look at a seasonal MA process. Okay, a seasonal MA process has that autocovariance function is AT minus capital theta AT minus E, right? Remember that it's an MA1, a seasonal MA1 process, or a SARIMA 0, 0, 1 with seasonality E. Okay, so the autoregressive polynomial is 1, that's it, and we have ZT tilde is equal to 1 minus theta times B AT, that's equal to AT minus theta AT minus 1. Okay, that's the that's what ZT is. Now to compute the variance is the expected value of this thing as squared. Okay, the variance gamma 0 is the expected value of what? Of 1 minus capital theta B squared, right? So it's equal to the expected value of 1 minus theta AT minus, sorry, it's 18. And I'm gonna write it down here. It's the expected value of AT minus capital theta AT minus 1, this whole thing squared. And again, I just square things, and that'll give me expected value of AT squared minus, and then 2 times capital theta AT minus 1 plus capital theta squared. Let's square. I'm going to, yeah, square times AT squared. Okay, and that again, this is expected value of AT squared is sigma squared, and then I have theta, capital theta squared times sigma squared, and this is going to be 0, right? Because AT and AT minus 1 are independent, they have mean 0. So I'm going to have 1 plus capital theta squared times sigma squared, that's the variance. And then I can also compute the covariance the same way we did it earlier, just replace the equation for ZT and ZT minus E, and ZT and ZT minus 2E, and so on. You'll see that the gamma sub E, that is the covariance between ZT and ZT minus E, is going to be minus theta sigma squared. And for every other value of K, gamma sub K will be equal to 0, which is what happens also in an MA1 process. Okay, in an MA1 process, the autocovariance is just has one lag that's different from 0, and the rest are 0. So the autocorrelation will be the autocovariance divided by the variance, and that will be minus capital theta divided by 1 plus theta squared for K is equal to E. So only at the E period, if the seasonality is E, we'll have a different value from rho, and then rho will be 0. The autocorrelation will be 0 for K different from E. Okay. Again, is it clear how to arrive to this thing now?
Yes.
Okay, good. So that's the autocorrelation. So the behavior then, if you look at an MA1 in a S seasonal MA1, the MA1, and let's suppose that the seasonality here is 4. Then for the MA1, you'll have the autocorrelation function would look like this. For example, let's suppose that row, that phi, in this case, in the MA1 is equal to 0.4 or let's say 0.5. It has to be less than 0.5, right? Remember? So I have an AR1, MA1. Oh, I erased it. I erased the whole thing and I shouldn't have erased the whole thing. We have an MA1 and I have a SMA1 with seasonality 4. The autocorrelation function for this one would be, I have one here, and it's like 1, like 2, like 3, like 4. And the MA1 will only take a value different from 0 for the first lag. So if it's probably something like this, and then it will be zeros for an MA1. The seasonal moving average, it'll behave exactly the same, except that the significant lag, the lag that's different from 0, will occur at the period of seasonality, 1, 2, 3, and then it'll be 4. Okay, and the rest are zeros. So for a moving average, a seasonal moving average model, the behavior will be very similar to the behavior of a moving average model, a non-seasonal moving average model. The difference is where the autocorrelation that is different from 0 lie. Okay. Now from here, can you imagine how the autocorrelation function, if you had a seasonal MA2 with seasonality 4? Okay, how do you think the autocorrelation function would look like for a seasonal MA2? In an MA2, in a non-seasonal MA2, the first 2 lags are different from 0 and the rest are 0. Well, for a seasonal MA2, it's going to be similar, except that it only happened that if let's suppose that is equal to 4, so we'll have something like this: 1, 2, 3, and then 4. Let's say this is negative in this case, and then 5, 6, 7, and 8. It will alternate signs because the coefficient is negative, and that's it. And the rest is going to be 0. So when we see something like this, that tells us that it's a seasonal model with a seasonality equal to 4. Okay. That's this example. With this model here, AT times 0.6 AT minus 4, and then we would have this. The autocorrelation function will be the minus 0.4 here in lag 4, and then it'll be 0 otherwise. Okay, it'll be 0 otherwise.
Why is negative if in the model it's positive? Like we have to equal to 0 the equation, or?
Yeah, what happens is, remember, ZT is minus capital theta AT minus C. So if capital theta, this is actually minus 4. This should be 0.4. Okay, this should be 0.4. No, that's right. It's 0.6 divided by, because the 1 minus 0.6, yeah. So in this particular example, capital phi is equal to minus 0.6. Okay, so that I have, what happens is that I have a mistake here. It should be 80 plus. Okay, I have a plus missing here. I missed a plus sign here. Is plus. Okay, but remember the formula is 80 minus capital theta. So capital theta is minus 0.6. And then the
Okay.
first autocorrelation is negative, and that's it. The rest are zero. Okay?
Thank you.
No, you're welcome. I'm glad you noticed that. So I hadn't noticed that I missed the plus sign. Okay. Now, unfortunately, things are not so beautiful with real series, and we very seldom have a series that's purely seasonal. We normally have some non-seasonal behavior together with a seasonal behavior. So that's why we use the multiplicative models. Box and Jenkins proposed the following model. Box and Jenkins said, okay, let's, since not all series are purely seasonal, then if I use a purely seasonal model, then what I'm going to get here, this alpha t is not going to be white noise because the model, the series is not purely seasonal. But I'm going to assume that I can model the seasonal part like with this, something like this. So I have seasonality E, and I have the dth difference, the dth seasonal difference applied to CT is theta of B to the E alpha t. What's different here is that what Box and Jenkins said, well, if the model is not purely seasonal, I can write the model like this, but alpha t will not be white noise. And I will assume then that alpha t is generated by an ARIMA model with parameters PDQ. So alpha t will now be an ARIMA model with parameters PDQ. And then I can write, since this is an ARIMA model PDQ, I can write alpha t with, I can model it like this, right? Because if alpha t has an ARIMA PDQ, then lowercase phi b, the dth difference of alpha t equal theta b of at, where at now is white noise. Okay, so this is the seasonal model, but this is not white noise, and then this alpha t behaves like this, like an ARIMA model. Okay, then if you put together the two expressions, that leads to the multiplicative model that was proposed by Box and Jenkins to model the seasonal time series that have seasonal components and also have non-seasonal components. And it's called a multiplicative because essentially we're taking we're multiplying the autoregressive polynomial times the seasonal autoregressive polynomial, seasonal autoregressive, with the moving average and the seasonal moving average polynomial. And I'm also multiplying here the differences, the standard differences and the seasonal differences. And we denote this model by a ARIMA of orders PDQ with lowercase. So this is always for the non-seasonal component. And capital P, capital Q with a subindex E for the seasonal component. And that's the ARIMA model of orders PDQ, capital P, capital D, capital Q, and seasonality E. Okay. Now, definitely, if you just looking at the model, you can realize that the autocorrelation structure of the model is going to be different. It's going to be more complex than a purely seasonal model or a purely non-seasonal model. So the behavior of the autocorrelation function will be more complex. Let's consider a simple case. So we have the series WT, which is a series that can be represented as a moving average, a non-seasonal moving average, and a seasonal moving average component. So we do not have an autoregressive term here. We do not have an autoregressive polynomial. Then if I write, this will be a ARIMA sticking to the notation, that will be a Sarima of orders. P is 0, D is equal to 0, and Q is equal to 1, 0, 0, 1, of seasonality 12. Okay, that will be the right notation for this model here. Because I have 0 terms, 0 autoregressive terms, 0 differences, 0 autoregressive seasonal terms, 0 seasonal differences, and I only have 1 moving average term and 1 moving average, 1 seasonal moving average term. Okay. So if I develop what this, do the computations here, take WT is equals to this times this, which are the 2 moving average polynomials. This is what I get. And I can use that now to study the autocorrelation function and the autocovariance function. Again, for that model, gamma 0 is the variance, and since we subtracted the mean, the variance is expected value of WT squared. So if you take this polynomial like this and square it, you're going to get the gamma 0 will be the expected value of AT minus theta AT minus 1 minus capital theta AT minus 12 plus theta capital theta AT minus 13 squared. And that's what I have here in the next slide. If you square that polynomial, what you get is that will be the expected value of AT squared plus theta squared expected value of AT minus 1 squared plus capital theta squared times expected value of AT minus 12 plus theta squared times capital theta squared expected value of AT minus 13. And you can group things here, and this will give you that sigma squared times 1 plus theta squared plus capital theta squared plus theta squared times capital theta squared. And that's essentially 1 plus 5 plus theta squared times 1 plus capital theta squared times sigma squared. That will be the variance of WT. And the covariance of order 1, that is 1 lag apart, the covariance will be the expected value of WT times WT minus 1. And if you replace again what WT is and what WT minus 1 is and do the algebra, you will get that this is minus theta times 1 plus capital theta squared times sigma squared. Just do the algebra, right? Just a matter of doing the algebra once you replace WT and WT minus 1 by their respective polynomials. You will find out also that gamma 2 is equal to 0. The autocovariance between ZT and ZT minus 2 is going to be equal to 0. And it will keep going equal to 0 up to gamma 10. Gamma 10 will still be equal to 0. Here, remember, we have E is equal to 12 in this case, remember. Okay, so gamma 10 is 0. The ones that are going to be different from 0 are gamma 11, because gamma 11 involves ZT minus 11 and ZT minus 12. So that'll be theta, capital theta times sigma squared. That'll be gamma 11. Gamma 12 will also be different from 0. Okay, gamma 12 will also be different from 0, and it will be minus capital theta times 1 plus theta squared sigma squared. And gamma 13 will also be different from 0, and the rest are going to be 0. So from here, from this point on, all the autocorrelation, all the autocovariances are going to be 0. So the only 3 autocovariances that are different from 0 are the first autocovariant, because of the first order non-seasonal moving average term. And then the 11th, the 12th, and the 13th autocovariance are going to be different from 0. If you compute the autocorrelations, then just divide the autocovariance by the variance, and that's what you get for the autocorrelations. So row 1 is different from 0. Row 11, row 12, and row 13 will be different from 0, and the rest will be equal to 0. Okay. Again, it's just a matter of algebra and doing the different cases. You can pick a couple of cases for k equals to, for example, you can try to compute row 2, row 3, and you'll see that up to this autocorrelations will keep going different, will keep being equal to 0 for every k up to the point where you get to the 11 lags apart, 12 and 13 lags apart, because of the seasonality of 12 lags. See, let's take this as an example. This is AT minus 0.5 AT minus 1, minus 0.4 AT minus 2, minus 0.2 AT minus 3. Okay. Plus 0.2 plus minus 0.2 AT minus 3. This is how it would look. The autocorrelation function would look like this. Lag 1 is always 1. We don't care about the lag 0 is equal to, I don't know, I didn't print the graph for 0 will be equal to 1. Depending on the solver you're using, if it gives you the 0, then for 0 it will always be equal to 1. Okay. But then, as you can see here, the only autocorrelations that are different from 0 are the first, the 11th, 12th, and the 13th, because of the station. The seasonality is equal to 12. What do you think would happen if the seasonality was equal to 4? You would have the first different from 0, the first autocorrelation, and then you would have the third, the fourth, and the fifth autocorrelations different from 0, and the rest will be 0, because that is a purely MA model. Remember that in pure MA models, in non-seasonal pure MA models, the autocorrelation function is only going to be different from 0, depending on the order of the moving average polynomial. Well, here you have two polynomials, two moving average polynomials, one seasonal and one non-seasonal. Okay. So, but the behavior indicates right away that we have very likely a model that has a seasonal component and a non-seasonal component. Let's look at an ARMA. This will be what? This will be a SARIMA of orders 1, 0. I'm not taking any difference. 0, because I don't have 0. I have 0 moving average terms on the non-seasonal component, times on the other side we have a moving average term, so it will be 0, 0, 1, and then seasonality 12. Remember, always indicate the seasonality when you use this notation, because it's important to know what the seasonality is. So for this model, again, I will not go through the algebra. It's just algebra. It's just replacing what WT is and computing the expectation WT times WT minus 1 times WT for the variance, and times WT minus 1 for the covariance for the 1, WT times WT minus 2 for covariance for the 2, and so on, up to 11, 12, and so on. Now, the behavior is going to be different because now I have an autoregressive term. Since I have autoregressive terms, that will tell me that the the behavior of the autocorrelation function will reflect that, and there will be the equivalent of the partial autocorrelation function that will tell us which type of model we have. See that the autocovariance behavior is similar to a non-seasonal AR1. If remember for the AR purely seasonal AR model, the behavior of the autocovariance was very similar to the behavior of the autocovariance for a non-seasonal AR. For a pure MA model, the same thing happens. Okay, for the behavior for the autocorrelation function of the seasonal component of the seasonal model was very similar to the behavior of the autocorrelation function of the non-seasonal model, MA non-seasonal model. The same thing is going to happen here. After 12 lags, the autocovariance behavior is going to be similar to the non-seasonal AR1 after 12 lags apart. Why 12? Because the seasonality is 12. So you will see something like this happening. This is the theoretical autocorrelation function. So for a model like this, which is an AR Sarima 100001 seasonality 12, the autocorrelation function would look like this. We'll have a significant lags different from 0 all over the place. Okay, here we do not have a. If it was purely MA, we would have exactly 0 for the theoretical autocorrelations, but it's not a pure MA process. It's an AR MA process with seasonal components. So for this particular model, this is how it would look, the autocorrelation function. So you can see here that there is something happening at lags 10, 11, 12, 13, and then you see that it's essentially dying there. Okay. Now it's going to be more difficult now to identify the type of models. The important thing is to detect. One thing is to detect the seasonality. What's the seasonality in my data? Because that will be key to developing or to identifying the right model for my series. Okay, so the only way we will not develop the autocorrelation function for more complex models because it's just a bunch of algebra, and the behavior of the pure, just looking at the autocorrelation function will not help us determine the order of the models. We need to look at both the autocorrelation function, the partial autocorrelation function, and we will see that the behavior of both will tell us if we have a seasonal component that's autoregressive or a seasonal component that's moving average and so on. And we'll learn that doing examples. That's where we are going to learn that by doing different examples. Okay. Now I don't think I'll have time to go over the script. I'll go very quickly. Let's see, it's 9:44 and I have to leave you. I have to let you go. Next, tomorrow we'll see it's a very short presentation of the model construction process, okay? How we construct Sarima models. It's a very short presentation because we'll do more exercises, because that's the only way to learn how to construct Sarima models is to do a bunch of exercises and try to identify the model, fit the model, and check the diagnostics. The way we check the diagnostics is going to be exactly the same. That doesn't change because the assumptions are the same. The assumption of this model, of this multiplicative model that we saw here, the assumption of this model is that these ATs are white noise. So the way we check the assumptions once we fit a seasonal model is the same way that we check the assumptions with non-seasonal models. Okay, so let's quit here. Are there any questions?